good job of explaining on one of our PPCs was how to find the right answer. So we're looking for that. This would be more of a multiple choice question. I'm fairly certain that you wouldn't. I'm really certain you wouldn't have anything like this. Listen to the video, see what they tell you, but I haven't ever seen a summation on any of the tests that I've been able to see. So what you're looking at, this summation notation is a way for us to add up all of the rectangles basically, and it's just a way to give a computation to anybody who wants to look at it written in writing, as opposed to just talking about three Riemann sums added together. So the idea is that we're still finding the area of all these rectangles, right? Which is still going to be change in x times f of whatever the x is, whether you choose left or right or whatever. So we're still looking at that. We're adding up rectangles, but let's see if we can put in the notation to represent all of them without writing each one out. So width of the rectangle is going to be b minus a over n. What does n mean? Number of rectangles. Number of rectangles. So you're going to look for that in the notation. If you look at the very bottom down here, that's this part. That's changing of x. So you want to look for that. This is what I was just saying Leland found on our PPCs, where he said, hey, look, if we're looking at this from 0 to 2, that has to be 2 over n. So that notation I want to be the most obvious for you. Okay, then each step in the interval, back up to the top, we're looking at a plus change of x times k. So a represents the starting value, right, of the integral, where it's starting. So this is going to be a, and then the ending here is b. And so we're looking at having this addition as part of our x1 value. Because if we don't start at 0, then we have to move it, right? We have to consider where a is and then move it. So we've got the width of each rectangle they've talked about right here, each step on the integral, and this one, it starts with 0, so that's not very exciting. But the last example, they start with 0. Wish they started with something else for our example. So this is a, this is the start. And then if we were doing this by hand, then we would think about, okay, if I'm starting here, the next one has to be a change of x away, right? So the first one's going to be 1 change of x away. The next one's going to be the second change of x away, like 2, 3, 4, 5, how many subintervals we have. That's what the k does for us. So the k is the step along the way. So this is like each new rectangle. Yep. So that will tell you the height. Because the change of x is going to be the same. In this sort of notation, you're not going to have a chart with different change of x's. We've seen those charts with different change of x's. But in this case, they have to all be the same for this to work. Because we have to go from this one to the next one to the next one. They have to be all the same. So in order for us to get the height at each of those, because these all had different heights, we have to figure out the function value. So this is height at that k value. At what iteration of change of x are you on? Does that make sense? Okay. And then the area is going to be the height times the width. This is the function. The function was 4 minus x squared. And this told us where we were on x. That was the step above right here. So things you can look for, these are mostly multiple choice questions. Considering looking at the function itself, and we started at 0, right? So this didn't change, it stayed at 4. I remember from those PPCs where it started at 1, and so this would have been 5. Does that make sense? Like if the integral said from 1 to something else, 1 to 3, in this case, if we're saying it's going to be 2 over n right here, it could be 1 to 3, and then that would have changed this part to 5, because it would have been this value plus 1 right here. But this one started at 0, so it didn't have any change there. So things you're looking for are what the a and the b are to find the change in x, and also how that changes your function value here in the multiple choice. So I want you to keep this as a reference. They're using, they've got some examples. If you look at your stuff that you're doing for me for the next 2 days, they have on day 3, I think. Day 3. Is that right? Does anybody see it? Okay, not day 3. I swear I just saw it. Oh, I'll find where I found it. Day 3. Okay, maybe not. Maybe I was looking at the one from yesterday. Did y'all do any already that had summation notation on the videos? Okay, well, I don't see it right now, but I swear I just saw it earlier today. So put this as a reference in your folder, and then you can kind of pick out the most important bits and pieces of those. The reason that we have the limit here is because we're adding up infinitely small ones, infinitely small rectangles. And so that's why we have the limit added to the summation notation. So instead of saying we have 4, we would have an infinite number of them. Okay, so we're adding that to our stuff. And then let's look at the volume card sort from last Monday. So we're looking at that volume card sort from last Monday. Problem 1 and 2 weren't that bad. I don't know what questions, like Caroline, you said you had some questions. Do you want to point me towards particular problem sets? It can be whatever. I got them all. 3B. Okay, so we're looking at 3B as a start. So 3B was the wrong one of the group. So what they told us is the student response. Oh, I'm wrong. 3B. 3B was the right one. Okay, so 3B, this is where I am. 3A was wrong, yes. Sorry, I had 2 up there and I still had 2 in my mind, and that's not what I should have had. Trying to see it all. All right, so find the volume of a solid generated when R is revolved around the horizontal line y equals -1. So if we draw that in, and they've just got big R there, can you see it? So we're not revolving this, just R. So we have to get that part first. How's that? Does that make sense? All right, so I do want you to practice, and if I was in my room with my boards, y'all would be drawing this all over those boards and making sense out of it that way. But instead, just draw it on paper. It is more interesting when y'all draw it and share with each other how you see the problem. But anyway, here's what we've got. It looks like this. And we're revolving it around y equals -1. So it's going to go, this point is going to go all the way around and be down here. This point's going to go to here. I've got a straight line in the middle. So it's going to look like almost like a funnel, I guess, because there's a hole in the top and the bottom. So it's good to picture what it is. It has a solid part, and then it has a non-solid part in the middle. It looks like a washer. Can you see my washer? It's not that bad. So what we have to do when we're figuring out the volume of the solid is that first it's good to recognize that -1 is not one of the, it doesn't meet at any of the points. Does that make sense? It's not connected to the graph at all, which means we're going to have to use subtraction with -1 in both of our different pi r squareds. Okay, so what we need to consider is that, and then the I'm going to use the notation they've used maybe here, maybe somewhere else. I think definitely on AP Classroom, where they say we've got pi r squared minus pi little r squared. And this is notation for the washer method, where, and I drew this as like solid circles and open circles before, but we have the solid part of our shape, and then we're subtracting the whole. Okay, so big R is this outside part of the washer that's going to be solid, and then we're going to subtract out the radius of the inside. So when I draw my washer, I'm going to have this, I guess actually this distance to be the big R, and then this distance to be the little r. So that's what I'm subtracting out. So what is the radius to the round circle? I need it to be this entire distance from this line up to this shape. What function is this one? F of x, right? I mean, like looking at the graph, like you'd have to look at your paper if you still have it. So f of x all the way down. So f of x would go to my x-axis, which is here, but I need to go all the way to -1. So we need to subtract the top minus the bottom, and the bottom is -1. So it ends up being f of x plus 1. That's the radius. So that's going to be squared with the pi in the front. And I do want you to write pi r squared, so that you consider you have to square it, and that you include pi. So that's the first part, and I'll write it here. So I've got pi, and then I'm going to have this. Well, I'm going to write it twice. I'm going to have, actually without the integral, pi r squared minus pi little r squared. So pi, and then big R is f of x minus -1, so plus 1 squared. And that's the whole radius. So it's squared. So that's the circle. And then we're going to subtract out the hole that gets born out of the inside. And it's going to be little radius, which is the other function, to -1. That's g. That's going to be g of x minus -1 plus 1 all squared dx from 0 to 3. 0 to 3. Because this went from 0 and this value here is 3. Because it gave me that point. That's convenient. So it goes around like that. So seeing it as pi r squared minus pi r squared, because it's not connected to the line y equals -1. That's supposed to be helpful. Carolyn? So when we did area of just this piece, which you can't see, area of this piece, we said top minus bottom, right? When we're talking about this new picture that is now discombobulated, and I'm going from here to here, I'm bypassing this one, okay? It's a separate circle. If this was a solid bowl without an inside cut out, then I would disregard this other little, oh, it's supposed to be straight. But anyway, I would say the top minus the bottom. And the top is f of x, and the bottom is -1. So we do subtract the bottom. It's just that the bottom is -1. So what happens is, because you subtract, it changes this to be addition. What you have is the total height here, that's f of x, and then you add the height here. You've opposited this because it's negative, and so now you have the entire height. I don't know how to do that better. So revolving around a place that's not connected is going to have this look to it where there are two separate pi r squareds and little pi r squared. That's the subtracting out part. Is there another one on here that we should look at that's similar? Do you want to try again? Like 4 or 5 or 6? Or 4 or 5 or 6 that you have other questions for? How about like 6 that they all went the other way? Except for one of them, right? Because it had this crazy shape that looks like it's separated, but you could look at it this way, top to bottom. You let me know what ones you need to go look at. I gave you solutions. Yep. Oh, you found it. Okay. So day 3 thing, sigma notation. So they're going to go through that in the first one that you go through. 6 do B. So Charlotte, I'm going to leave that, and if y'all have questions after the video, that sigma 1, but thank you for finding it, because I thought it really could, it was there. No, you have made it so I'm not needing that insane questions test yet. All right, so 6B, you said? I'm going to circle it so I don't forget. Okay, find the volume of the solid generated when R is revolved around the x-axis. So if it's revolved around the x-axis, it's connected, that's good. It's going to look like this. Oh, that connects. And then opposite here, this sort of looks like a jellyfish. And we're revolving around the x-axis, so our circles go this way. And so it's perpendicular to which one? It's perpendicular to the x-axis. So if you drew like your circle that it had a width to it, this would be dx. So that's what helps me figure out whether it's an x and y for sure. So the circle is with regard to going around the x-axis, so it's dx. When I draw this like a slice of cheese or whatever you would slice, it would have some width, and that's change in x going this way. So everything needs to be an x. And we've got two different functions. We've got 1 minus x, that's here, with a square root, and 1 plus x squared, I'm sorry, x plus 1 squared, here. Whoopsies, sorry. So are y'all able to figure out which function is which looking at it? So this looks like half parabola. This looks like square root, but it's backwards because of the minus x there. It's a flip. So that's going to be important, right? You're going to have to know what they are, and that's pre-calculus stuff coming into play. So these circles are dependent on what function you have. So I'm going to move this down so I can still see it. So my integral, how do I need to do that? I need to do, so this is going to be a circle, so pi r squared. But what happens between these two places? Right, this circle is dependent on the radius being this function, whereas this is going to be something different. You might call this, I don't know, y2 squared, and this y1 squared. Like they're two different We're not subtracting them, but the circle slices over here are dependent on x plus 1 squared. The circles over here are dependent on 1 minus x squared. So we have to separate it that way. So I would say we've got pi r squared plus pi r squared. And we're going from -1 to 0 with this first radius, and we have to recognize what it is. I guess it doesn't really matter in this case, because as long as you did, no, it does, because 0 to 1, it would be this function. Sorry, because I need these values. X plus 1, sometimes you got to say stuff out loud so it makes sense or not. So that represents all of these circles, right? So these circles are dependent on x plus 1 squared, and there's no subtraction because it's connected to this. So then we're going to add it to still pi. I got it separated because I have a new integral here with new values from 0. Wait, nobody corrected me here. I really meant -1 to 0. I needed this side, -1 to 0. And then I needed this side to be 0 to 1. And that would be the square root of 1 minus x squared dx. Yep. Oh, yeah, thank you. Okay, so this function is squared. So there it's squared again. Thank you. Yes. So it might be good to write down the radius equals x plus 1 squared, and then you see that's just r. Me and my old eyes, this all got connected for me, so writing down what the radius is helpful, especially with the ones that were like semicircles. That was the one, there was one problem like that, I feel like that might have been on the mock exam, where you had to consider if you were raising up semicircles from this. Is there such a thing in this problem? No. If you're doing semicircles, then you have to do the half, right? So this would be the whole function value, but in a semicircle you need 1/2 pi r squared. And so you need 1/2 for the semicircle, and then you need, the radius would have to be 1/2 of f of x squared. And that extra half was important because it's not the whole function value. That's not radius, that's diameter. So you had to figure out what the radius is, and it's half of the function. So you have like an extra half in there, and then it ends up being squared, so you've got 3 1/2. So it is good, thank you for that, Leland, to maybe write radius on its own so that if there's some, squared going on or square root, that you see it separately before you try to put it in the integral. Okay, that was a good one because it had separate ones. Others? So we have time this week to go through questions. Again, I want to pull out stuff for you to look at. We could possibly do the day 4 live tomorrow. You could watch it in class if you want to. We could just do it up here and you could take notes. It's up to you. Otherwise, you can bring earphones and then ask me questions separately. You let me know. Let me know now, because otherwise I'll plan something different. Okay, well, do it tomorrow. Okay. It's long. Yeah? Sure. So you can do it by yourselves. That way you can watch it in your own speed. That'll be fine. So otherwise, you can ask me questions. You should be working on, and some of you, it's not your favorite thing, so you don't want to do the one pager. Even this might be 2 pages, and I have like summaries that I could give you. It doesn't do any good for you to have a summary if you haven't made it on your own. If you're really just looking at somebody else's, I mean, it's a cram right beforehand, it's something. But if you have to go think about all the different stuff that you need on a summary, then there's a lot of thought that goes into that. And when you figure out how to write it down, when I do the ones that I've posted on the board, I didn't have it up this morning. I write it and then it's not good and I erase it and I try to do it better, and that helps me think about how I should present it to you, also how I should memorize it. So I would like for you to be adding to that one pager Monday, Tuesday, and Wednesday, and I'd like to look at them on Thursday, and I can put up a summary that somebody else has made, and you can say, oh, I don't have those things, and then we can try to add them to it. I'm going to print out the rest of the AP Lives as they happen, if they all happen before the seniors leave. But we won't have time to go through all of them before next week. So that gives you something to look at this weekend. There are some summaries from last year that I might pull out and suggest to you that would be past what I would grade for you, but would be something that you could do over the weekend and prepare. So, I mean, at this point, I don't want to stress you out by giving you so much that you feel like you can't get through it. I really want to give you manageable chunks where you go through problems and are like, okay, this I get. I'm going to go do the next thing, because it shouldn't be a cram session. We've covered everything and y'all have done a really good job with it this year. So it's a matter of making sure we have proper notation. We're getting little details down. We say that if we have an integral, we write it out, and then we say it's continuous if we're trying to write something. We should, maybe tomorrow we should do, I think it's on my list already for theorems to add to the one pager. So you should start your, so I've got theorem review tomorrow as my thought process for putting on your one pager. So we can look at all those and the things you would need to write down or not. And when they talk to you, do they say stuff like, okay, you could stop here, adding it through? They probably go through the answer completely, but to let you know where it is where you can be like, okay, I have answered this question and I can move on and use my time for something else. I could still get full credit for this even though I haven't told them F prime is 2 or whatever. So they assume anybody could put stuff into a calculator and check it. They want to see what calculus you know.